Welcome to part 2 of 17.4, why do chemical reactions take place? So in this part of the video, we're going to talk about Gibbs free energy. If you've not watched the video on entropy yet, you need to watch that before this one. Okay, so our learning objectives for today, we need to be able to explain what feasible means, explain how changes in entropy and enthalpy determine whether a reaction is feasible or not, and then be able to calculate Gibbs free energy. So first of all, what does feasible or spontaneous mean? So both these words are used interchangeably in chemistry. I'm going to use feasible because I don't like the word spontaneous, because spontaneous implies something that's definitely going to happen and it's just going to happen just like that. But as we'll see, if it's something's feasible or spontaneous, it doesn't mean it's necessarily going to happen. It just means it can happen. So I think the word feasible is better, but you might see the word spontaneous in an exam. So feasible means that a reaction can take place. So if a reaction is feasible, it means it can happen. Okay, but this is based on thermodynamics, so it's based on energetics. So just because thermodynamics says it can happen doesn't mean it will, which is why I take issue with the word spontaneous. So the reaction might still not take place. If there's a high activation energy, then the reaction won't happen. So the reaction might be so slow that effectively it doesn't take place. So for example, the reaction of graphite with oxygen is feasible, but we can all use our pencils without them spontaneously combusting, and that's because the reaction's effectively so slow that it doesn't take place because the activation energy is high. So we need to learn this equation. So Gibbs free energy is represented with the symbol capital G, and we've met the delta before to mean change. So a change in Gibbs free energy is equal to the enthalpy change minus the temperature times by the entropy change. And the Gibbs free energy is in kilojoules per mole, and the enthalpy change, as we know from our previous work, is in kilojoules per mole. The temperature, as we did in the previous work on the ideal gas equation, is in Kelvin. So if you get given it in degrees C, you need to convert it. Now, entropy is a tricky one, because if you've watched the entropy video, you'll know that entropy is measured in joules per mole per Kelvin. So when we calculate an entropy change, the final answer will be in joules per mole per Kelvin. So if we're going to put it into this equation, then we need to divide it by 1,000 to give it in kilojoules per mole per Kelvin. This is quite often a common mistake in exam questions. So we have to make sure that we convert it. So exam questions, they quite often get you to work out the entropy change and then use that in the Gibbs free energy equation. So we need to remember to convert it to kilojoules per mole per Kelvin. So the value of Gibbs free energy is useful because it tells us whether the reaction is feasible or not. So if delta G comes out as positive, then the reaction is not feasible, so it's not going to happen. If the change in Gibbs free energy comes out as negative, then the reaction is feasible. And then you've got this kind of in-between state. So if delta G is at 0, that means the system's in equilibrium. So it might be for a chemical reaction, but it also could be for a change of state. So if you have water evaporating to give water vapor, for example, then at the boiling point, where it's boiling and evaporating, that's going to be in equilibrium, because you'll have some water evaporating, but you'll also have some steam condensing. And at that point, the Gibbs free energy is 0. It's also the point at which the reaction becomes feasible, but we'll look at that later. So we need to look at how temperature affects the feasibility of the reaction. So if we look at Gibbs free energy, the equation for it, you can see that it's got an enthalpy term and it's got an entropy term. So where the entropy is times by the temperature. So the enthalpy, the entropy, and the temperature is important. So if I've got an exothermic reaction, and I've also got an increase in entropy. So if we look at that term, so remember, we want delta G to be negative for our reaction to be feasible. So if a reaction is exothermic, delta H is negative. And the increase in entropy means that delta S is positive. So the change in entropy is positive. So if the change in entropy is positive, then minus T delta S is going to be negative. So if delta H is negative and minus T delta S is going to be negative, then delta G has to be negative, because you've got a negative number minusing another number. So it's got to be negative. It doesn't matter what the temperature is, Gibbs free energy is going to be negative, and therefore the reaction's always going to be feasible. Doesn't matter what the temperature is, it's going to be feasible at any point. So if we've got an exothermic reaction, but it's got a decrease in entropy, then again, our enthalpy change, delta H, is negative. But this time, our minus T delta S is positive, because if delta S is negative, and temperature, because it's in Kelvin, has to be positive, then you're minusing a minus, and therefore minus T delta S has got to be positive. So therefore, you've got one negative, which is your delta H, and you've got one positive, which is your minus T delta S. So for it to be overall negative, you want the enthalpy term, so you want delta H to be bigger than T delta S. So what you want is a low temperature to make that T delta S small in value, so it's smaller than the delta H. So if you get to a higher temperature, then the T delta S term is going to be bigger than delta H, and it's going to end up positive. So for exothermic reactions with a decrease in entropy, it's going to be feasible at low temperatures. So if I've got an endothermic reaction, but an increase in entropy, then my delta H term is going to be positive. But because delta S is positive, the minus T delta S is going to be negative. So what we want here, because we want the overall term to be negative, we want the overall expression to be negative, we need the minus T delta S to be bigger than the delta H, because that's the only way that delta G is going to be negative overall. So for this reaction to be feasible, so for an endothermic reaction with an increase in entropy to be feasible, we need higher temperatures, because at higher temperatures, the T delta S is going to become larger than delta H, and therefore the negative value is larger, so delta G is going to be negative. So our last case that we could possibly have is an endothermic reaction with a decrease in entropy. So in this case, delta H is positive, but the minus T delta S is also positive. So if you've got two positive numbers, it doesn't matter what T is. It's always going to be positive, because you've got a positive and a second positive. So that reaction is never feasible. So you are never going to get a reaction which is endothermic and you have a decrease in entropy. It's just not thermodynamically possible. So if we're calculating Gibbs free energy, we need to use the equation that we've mentioned. And Gibbs free energy and enthalpy change, as we've mentioned, are in kilojoules per mole, temperatures in Kelvin, and the entropy is in kilojoules per mole per Kelvin. So we just need to remember, as I said before, to convert that from joules per mole per Kelvin divided by 1,000. I'm going to do a separate video where I talk you through a worked example. So you need to watch that for the calculating Gibbs free energy. There's another calculation that you might need to do. So sometimes you're asked to calculate the temperature at which a reaction becomes feasible. So because a reaction is feasible if delta G is negative, but it's not feasible if it's positive, then the point at which delta G is 0 is the point at which it swaps over from being feasible to not feasible, or the other way around, not feasible to feasible. So when it asks you to calculate the temperature at which a reaction becomes feasible, it's asking what the temperature is when delta G is 0. So if we put delta G is 0 into that equation, we get 0 equals delta H minus T delta S. And if we rearrange that, we get delta H equals T delta S. And then if we rearrange that further, that means the temperature is the enthalpy change divided by the entropy change. And again, we've got to remember to convert the entropy change into kilojoules per mole per Kelvin. Again, I'm going to be doing a worked example of one of these questions. So you can watch that video after you've watched this one. Okay, that's all you need to know for this video. Thank you for listening. See you next time.